All right, let's go.
Theory 7, the layered model, and why we got Jupiter's size wrong for 50 years. In February 2026, NASA published a paper in Nature Astronomy based on 13 complete flybys of Jupiter by the Juno spacecraft. The finding was immediate and surprising. Jupiter is 8 kilometers narrower at the equator and 24 kilometers flatter at the poles than every measurement made since the Pioneer and Voyager spacecraft flew past it in the 1970s. Every textbook published before 2026 has the wrong dimensions. The planet's mean radius is now confirmed at 69,886 kilometers, 8 kilometers smaller than previously calculated. Eli Galante at the Weizmann Institute of Science stated it directly. These few kilometers matter. Small shifts in radius change the entire gravity model, and the gravity model is the only tool scientists have for understanding what is happening inside a planet nobody has ever seen into. That is the central problem with Jupiter. It is the largest planet in the solar system. 1,300 Earths fit inside it. It has been stared at for centuries, and no probe has ever penetrated more than 150 kilometers below its cloud tops before being crushed by pressure. The planet is 69,886 kilometers in radius. We have seen 150 of those kilometers. Everything below is inferred from gravity measurements taken by spacecraft flying past the outside. Before Juno arrived in 2016, the standard model had 4 distinct layers: atmosphere at the top, molecular hydrogen below it, metallic hydrogen further down, rocky core at the center. Clean, layered, sharp boundaries between each zone. The model was built on known physics. At the surface, hydrogen is a gas. Under increasing pressure going deeper, it becomes a liquid. At approximately 7,000 kilometers below the cloud tops, the pressure reaches 1.4 megabars, 1.4 million times Earth's atmospheric pressure. At this threshold, hydrogen undergoes a fundamental transformation. Its electrons decouple from individual atoms and move freely through the fluid, the way electrons move through metal. Hydrogen becomes electrically conductive, metallic hydrogen. This state of matter does not exist naturally anywhere on Earth. Physicists have produced it in laboratories using explosive compression for fractions of a second before the equipment is destroyed. Inside Jupiter, it exists in a stable layer extending from 7,000 kilometers deep all the way toward the center. The movement of this conducting fluid generates Jupiter's magnetic field, the strongest planetary magnetic field in the solar system, roughly 10 times stronger than Earth's. Below the metallic hydrogen, the old model placed a compact rocky core, 10 to 15 Earth masses, solid, distinct, sitting at the center at temperatures around 35,000 Kelvin, hotter than the surface of the Sun. Juno measured the gravitational field with unprecedented precision. The data did not fit this picture. The bottom half of the layered model was wrong.
Theory 6, the fuzzy core, the most significant planetary science discovery of the last decade. The gravity harmonics Juno measured, subtle variations in Jupiter's gravitational pull during each flyby, were inconsistent with a small, compact, rocky core surrounded by sharp boundaries. Instead of a distinct rocky center surrounded by clean layers of gas, Jupiter's core gradually blends into the hydrogen-rich layers above it. No sharp boundary, a smooth transition zone. Heavy elements, rock, ice, carbon compounds, mixed into hydrogen throughout an enormous diffuse region, extending potentially 20,000 to 30,000 kilometers outward from the center. Not a compact ball sitting at the bottom, an enormous gradient where the concentration of heavy elements slowly thins out as you move upward toward the outer envelope. Jupiter's interior also has a non-uniform distribution of heavy elements throughout. More metallic enrichment in the deeper regions, less in the outer layers. A gradual composition profile from center to surface. Nothing like the clean boundaries the pre-Juno model assumed. Scientists call this the fuzzy core, or the dilute core. The terminology is deliberate. The core is not absent, but it is not what anyone expected. This discovery matters for planetary science formation in a direct and unresolved way.
The standard model of how gas giants form, called core accretion, requires a solid rocky core to first accumulate enough mass to gravitationally pull in hydrogen and helium from the surrounding disk. A fuzzy dilute core does not fit that story cleanly. Either the core formed solid and was subsequently disrupted, or it was never sharply defined to begin with. Both scenarios require explanation.
Theory 5. The giant impact hypothesis. A protoplanet smashed into Jupiter and mixed everything. One proposed explanation for the fuzzy core was a catastrophic collision early in Jupiter's history. Not an asteroid, a protoplanet. Something with the mass of several Earths, moving at tens of kilometers per second, plunging through Jupiter's outer hydrogen envelope and striking the rocky core directly. The collision would have been so energetic that core material was partially vaporized, mixed with the surrounding hydrogen, distributed outward into layers above the core, the sharp boundary between core and envelope erased in a single event, a diffuse gradient left behind. This was a compelling hypothesis. Giant impacts are well confirmed in the early solar system. Theia hit the early Earth and produced the Moon. Another impactor hit Uranus and knocked it 98 degrees onto its side. Jupiter receiving a major impact during the same chaotic period was not implausible. Then, in July 2025, a team from Durham University working with NASA ran the most detailed computer simulations of the scenario ever attempted. Advanced fluid dynamics modeling that tracked how rocky and hydrogen-rich material mixed together during a giant impact. They ran it multiple ways: different impactor masses, different collision angles, different velocities. The results were clear and unexpected. In every simulation, the dense, rocky core material rapidly resettled after impact. It sank back down and reformed a core with a sharp boundary, exactly the opposite of what Juno observed. None of the simulations produced a stable, dilute core matching Jupiter's real interior. The giant impact hypothesis was published in monthly notices of the Royal Astronomical Society in July 2025, and the conclusion was direct. Whatever created the fuzzy core, it was not a giant impact.
Theory 4. Primordial mixing and convective erosion. The core was never sharp to begin with. If impacts did not create the fuzzy core, then the explanation has to be found in Jupiter's formation and evolution itself. The primordial mixing hypothesis proposes that during Jupiter's formation, the core was never cleanly separated from the surrounding hydrogen. As hydrogen and helium collapsed inward onto the forming planet, the infalling material carried enormous thermal energy. The proto-Jupiter was hot, possibly hot enough that rocky and icy material settling toward the center remained in a semi-fluid state rather than solidifying into a compact ball. Rock and hydrogen mixing together during formation, a diffuse distribution present from the very beginning. A second mechanism is convective erosion. Even if a solid core did form early, the extreme heat of Jupiter's interior drives powerful convective currents, large-scale circulation patterns in which hotter material rises and cooler material sinks. These currents carry momentum. Over 4.5 billion years, they could mechanically erode a once compact core, gradually breaking material off the boundary and distributing it upward into the surrounding hydrogen envelope. Not a single catastrophic event, continuous slow erosion across geological timescales. Juno's data also revealed that the temperature distribution inside Jupiter does not follow the simple gradient the old model predicted. The interior is more complex in its thermal structure, multiple zones with different temperature profiles, composition gradients that affect how energy moves. The standard adiabatic model, where temperature decreases smoothly and uniformly with distance from the center, does not fit the observations. The most current understanding, as of 2026, is a combination. Jupiter's core was probably never sharply defined, and 4.5 billion years of internal dynamics have continued to mix and redistribute its heavy elements. The fuzzy core is the result of both formation history and ongoing evolution. Not one event, the entire life of the planet.
Theory 3. Helium Rain. Liquid metal raining downward through the interior right now.
One of the strangest ongoing processes inside Jupiter has nothing to do with the core. In Jupiter's outer layers, helium mixes uniformly with hydrogen, the same way salt dissolves completely in water at room temperature. At the pressures and temperatures of the outer envelope, the two elements are fully miscible. They stay mixed. Going deeper into the metallic hydrogen layer, the conditions change. At a specific pressure and temperature threshold, helium becomes immiscible with metallic hydrogen, the same way oil becomes immiscible with water when you shake them and then watch them separate back out. The helium stops dissolving. It begins forming droplets. Those droplets are denser than the surrounding metallic hydrogen. They sink. Helium rains downward through the interior toward the deeper regions. As it falls, it releases gravitational potential energy. That energy becomes heat. This helium rain is not theoretical speculation. It is required by an observation. Jupiter radiates significantly more heat than it receives from the Sun, approximately 1.67 times as much. The planet is generating its own internal heat, far in excess of what residual formation heat can account for. Helium rain falling through the interior and releasing gravitational energy provides the additional heat source needed to close that gap. The Galileo probe descended into Jupiter's atmosphere in December 1995 and measured helium concentration directly. It was lower than expected from solar composition. Helium is missing from Jupiter's outer envelope. It has rained out, fallen into the interior. The measurement confirmed the process is real, active, ongoing right now as you watch this.
Theory 2. Diamond rain. Precious stones falling through the interior of the largest planet. This one sounds like it belongs in a different kind of video. The physics says otherwise. Jupiter's atmosphere contains methane, a carbon-hydrogen compound. Under the extreme pressures found below the cloud tops, methane decomposes. The hydrogen strips away from the carbon atoms. Free carbon is left behind. Under enormous pressure at depths of several thousand kilometers, that pressure compresses the carbon into graphite. Under even higher pressure further down, graphite is compressed further into diamond. Physicists Mona Delitsky and Kevin Baines first calculated the conditions for this in 2013. Their model predicted that inside Jupiter and Saturn, carbon is converted into diamond crystals that then fall through the interior, sinking through layers of liquid hydrogen, growing larger as they descend by accumulating more carbon from the surrounding material, before eventually reaching depths where the pressure and temperature are so extreme that even diamond becomes unstable, where it melts into a liquid carbon ocean at the bottom, near the center that no instrument has ever detected and no probe will reach in any foreseeable future. Theory 1. What we still do not know. The questions Juno could not answer after a decade of orbiting. Juno launched in 2011, arrived at Jupiter in 2016, completed over 60 close polar orbits, measured the gravitational field to greater precision than any previous mission, measured the magnetic field, probed the deep atmosphere with microwave instruments, photographed the poles, detected lightning, tracked jet streams 3,000 kilometers below the cloud tops. NASA extended Juno's mission beyond its original 2021 end date through September 2025 because the data kept producing new questions. At the end of its mission, Juno was intentionally plunged into Jupiter's atmosphere, not because it stopped working, because the protocols for protecting the Galilean moons, Europa, Ganymede, and Callisto, from possible Earth microbe contamination required the spacecraft to be destroyed rather than drift uncontrolled to new worlds that may host life. A decade of orbiting, hundreds of gigabytes of data, the most detailed picture of Jupiter ever assembled, and these questions remain unanswered. Whether there is any solid nucleus at the absolute center of the fuzzy core, the gravitational signal from a small, solid remnant buried under 70,000 kilometers of planet is too weak for Juno to detect definitively. It may be there, it may not be, unknown. The global water abundance inside Jupiter, critical for understanding where in the early solar system Jupiter formed. The Galileo probe measured water at one location at 5 degrees north latitude. Whether that is representative of the planet as a whole requires assumptions about atmospheric dynamics that are still being debated. The precise composition of the fuzzy core region. Gravity measurements tell you density.
Multiple very different compositions could produce the same density. Without a sample from inside the fuzzy core, the breakdown between rock, ice, and carbon compounds cannot be determined. The mechanism that keeps the fuzzy core from settling back into a sharp boundary. Normal physics says denser material sinks and lighter material rises. Over time, that should produce a compact core with a sharp edge. Jupiter's interior has been doing the opposite for 4.5 billion years. Sustained mixing, sustained diffusion. The process maintaining that state is not agreed upon. No probe will descend into Jupiter's deep interior in any mission currently planned. The pressures involved are far beyond anything human engineering has ever designed for. The next major step in understanding what is inside Jupiter will come from more precise gravitational measurements from future spacecraft, and from laboratory experiments that push hydrogen and helium to ever higher pressures for ever longer durations. Until then, the interior of the largest planet in the solar system remains one of the most studied unknowns in planetary science. We can describe the outside with extraordinary precision. We have corrected the size of it as recently as February 2026, and we still cannot say with certainty what is sitting at the center.
7 theories. A layered model built on solid physics that Juno proved was wrong in its most important detail. A fuzzy, dilute core confirmed by gravity measurements that no one predicted and still no one fully explains. A giant impact hypothesis that the best simulations as of July 2025 ruled out completely. Primordial mixing and 4.5 billion years of convective erosion as the leading explanation for what the core actually is. Helium rain falling right now through the metallic hydrogen interior, releasing heat that keeps Jupiter warmer than the sun alone can make it. Diamond crystals possibly forming and falling toward a liquid carbon ocean at depths no instrument has ever reached. And a list of fundamental questions about the interior of the biggest planet in our solar system that a decade of precise orbital science could not resolve. We've been looking at Jupiter for 400 years. We corrected its size in 2026. We still do not know what is inside it. Subscribe to Cosmic Hives. See you in the next one.